Hello students, welcome to the video lecture series of structural analysis. Today we are going to discuss the important topic of your structural analysis, that is moving loads and influence line diagram. So what we study in this course, in this module, that first we'll learn how to construct a influence line diagram for simply supported beam with the different loading conditions. So what are the different loading conditions we have? Let's say the point loads. If there is a uniformly distributed load, basically we'll cover these two types of loads, the point loads and UDLs. And then we'll discuss about uh, how what will be the influence line diagram if a wheel load is moving in the simply supported beam. If a train load means a series of load is moving in the simply supported beam, we'll see different scenarios. And in the latter part of this module, we'll discuss about how to construct an influence line diagram in case of overhanging beams, in case of cantilever beams, and most important, how can we apply these influence line diagrams to the truss bridges. This is also important concept to understand. So once again, welcome to this course, and we'll enter into the moving loads. So what is moving loads? Let us just see this one video is playing in the right hand side of this screen. You can see that a load is moving, let's say on the breeze. Okay, because of the loads, what happens? What are the responses and varying on the breeze? Look into this. If the load is moving, so initially when load was there, the responses was, let's say this is the bending moment diagram. So the bending moment diagram is changing as the load is moving. That means the response is changing. It is not constant, right? So what we are calculating before? What we are calculating before? If there is a static load, let's say there is a beam, simply supported beam. Okay, there is a simply supported beam and a point load is there. So in that case, we are able to calculate what is the reaction at A, what is the reaction at B, what are the shear force under the loads, what are the bending moment under the loads. Okay, but now what happens? The load is moving. So let's say this is the breeze, and over the breeze, a different type of loads, different type of vehicles are moving. So because of different types of vehicles are moving, so they have a different impact on the breeze. So while designing the breeze, we have to keep in mind, we have to understand what is the response of the breeze due to the moving loads, right? So let's say earlier the load was here at point C, this is the point C, this is the end A and this is end B. So because of the point C, there will be a, because of the load at the point C, there will be a reaction at A and there will be another reaction at B. Now, after some times, what happens? This load is shifted to this particular point D, let's say. So, when the load is at location D, so this reaction will change. Yes or no? So this reaction will change at the same time, the reaction will also change. So now due to the moving loads, the reaction is changing. Similarly, your shear force under the loads will also change and bending moment under the loads will also change. So what we are going to understand in this particular concept, that we can understand the variation of structural responses due to the moving loads. So what are the variations of the, what are the structural responses? Structural response is nothing but your reaction. Structural response is nothing but a reaction, shear force, bending moment, or sometimes deflection. Okay, these are the structural responses, and we will understand how these responses are varying due to the moving loads. So that is how why influence line is now important. Okay, so why influence line is important? Because The structural responses changes as the load position changes, and this influence line is going to help us to identifying the critical load positions. What is that critical load positions where we are getting maximum shear force, where you are getting maximum bending moment? Okay, so it will help us to identifying the critical load position on the beam, right? So if you ask me what is influence line diagram, so influence line is nothing but it is a diagram that shows the variation of the response functions. What we have discussed now, what are the response functions? Reactions, shear force, bending moment, etc. at a specific point in a structure due to a unit moving load. So we are considering whatever load it is, we are considering it as a unit moving load, and due to this unit moving load, what is the variation in the responses? If we plot those variations, then we can call it influence line diagram. We can call it influence line diagram. So what is the purpose of the influence line? Again, if I ask you, to determine the maximum reactions, shear force and bending moment, we can locate the critical positions of moving loads and where it is used actually. It is widely used in the bridge design. And why it is important again? It is important, it is essential for the economical and safe design. So while designing the bridge, if you consider the moving loads, it will help us a economical and safe design, right? So how this influence line looks like, you can see. So now we are considering this load as a unit load. We're considering this load as a unit load. And now let's say this unit load is at this particular position, and how the influence line looks like. We'll see how the diagram is constructed. We'll see in the future slides. So now what happens? This unit load is moving from end A to end C. So when it is moving from end A to end C, there is a variation in the reactions. So this diagram is nothing but your influence line for reaction at A. We'll see how it is constructed. Okay. So when the unit load is reaching at point C, what will be the value of reaction at A? That we also see. So now you just see that how the influence line diagram looks like. Okay. Coming to the uh, case, how can we draw the influence line diagram for a simply supported beam with point load? So whatever the load, we have converted into point load, a unit load, right? So a unit load is moving from one end to other end. Okay. Let's say at this particular position, the distance from end A to unit point load, that is X. Okay, so how the influence the line diagram for reaction at A looks like? At A, the maximum unit will be there, and at B it will be 0. Similarly, the opposite for reaction at B. So this is the shear force at C. That's we are calculating shear force under C, and because of the unit load, how the ILD looks like for shear force at C, and this is the ILD for bending moment at C. We'll see now how it is the influence line is constructed. Coming to shear force, how can we construct the ILD for reaction at A? Now look into this particular condition. So here is the simply supported beam, that is AB, okay, and the point load, that is your unit load, is at X distance from A, okay, and the total length of the beam is L, and we are going to calculate, let's say at point C, which is distance at Z. So how to find out now? How to find out the reactions? How to calculate the reactions? We know how can we calculate the reaction? If we take moment at point A is equal to 0, if you take moment at point A is equal to 0, so what will be the equation now? Tell me. RB into L minus RB into L. So the force into perpendicular distance minus 1 into perpendicular distance is x is equal to 0. So now what will be RB? RB is equal to x by L. So RB we have calculated x by L. So what will be RA? So you know RA plus RB is equal to 1. So that means how to calculate RA? RA is equal to 1 minus RB. So 1 minus x by L. So it will be 1 minus x by L. So L minus x by L. So RA is equal to L minus x by L. Okay. Now let us construct the influence line. So we'll draw a table X and reaction at A. If you consider this L is equal to 1, the L is equal to 1 meter. So total length of the beam is 1 meter. Now, if X is equal to 0, what will be the reaction at A? So this is the equation RA is equal to L minus X by L. So if X is equal to 0, what will be the equation? Now L is 1. So 1 minus X by 1. So it will be X is equal to 0. So 1 by 1, it will be 1. Right? So if X is equal to 0.25, if X is equal to 0.25, now put the value here 0.25. So 1 minus 0.25 by 1. So 1 minus 0.25. So 0.75. Now put the value of X is equal to 0.5. So it will be also 0.5. Now put the value X is equal to 0.75. It will be 0.75. How much it will be? 1 minus 0.75 by 1. So that is 0.25. Now X is equal to 1. So what will be the value of reaction at A? 1 minus 1, that is 0. So this table we have calculated what will be the reaction at A when your unit load is moving from end A to end B, right? When X is equal to 0, that means your unit load is on point A, right? When X is equal to 0.25, somewhere here, right? When X is equal to 0.5, somewhere at the center. When X is equal to 0.75, somewhere here. When X is equal to 1, it will be on point B. So now your unit load is moving from end A to end B, and due to that moved positions, what is the value of reaction at A we have calculated? If you draw these values, if you construct these values, if you connect these values, so at A, X is equal to 0 means on the point A, what is the value? That is 1. At point 0.25, let's say this is 0.25. At 0.25, the value is, what is the ordinate? 0.75. X is equal to 0.5. So this ordinate is 0.5. At X is equal to 0.75, your ordinate will be 0.25. And X is equal to 1. So this is 0. If you connect those points, it will be a straight line. So now this is nothing but your influence line diagram for reaction at A. In the similar way, we can calculate another table X and reaction at B, and we'll get the exact opposite of these values. So that's why if you connect all these points at different locations, and if you draw, it will be also a straight line. That's opposite of the reaction at A. So this is ILD for reaction at A. This is ILD for reaction at B. I hope you understood this. Next, we'll move to how to find out or how to construct the shear force, the ILD for shear force at a particular point, let's say in this particular diagram, let's say we are calculating shear force at point C. How to construct the ILD for shear force at C and ILD for bending moment at C will see. So what is the reaction we have calculated here? L minus X by L, and reaction at B was X by L, right? So how to find out the, now we'll write the equation for shear force. So what will be the shear force at X at this particular position? Now let's say the unit load is at X distance from A. What will be the equation? Shear force at X. How many forces are there? So it will be, let's say, L minus X by L, right? Minus, so this is your shear force at X. So if you calculate shear force at C, the same position, let's say the condition is your unit load is, unit load is, let's say the not unit load is in between A and C. So X is in between 0 and Z. Unit load is in between A and C. So unit load is in between A and C. Okay, or we can write is the X value is in between 0 to Z, right? So in the same, that is both conditions are same. So how to find out the shear force at C? The shear force at C will be L minus X by L, L minus X by L. So RA, that is upward, so we have considered positive. L minus X by L minus the unit load 1, right? So what will be the equation? So instead of X, we'll write Z, because at C the value of X is Z. So L minus Z by L minus 1. So what will be this? L, L minus Z minus L. So L cancels out. So it will be minus Z by L. So shear force at C left, let's see, it will be minus Z by L. So similarly, when we calculate shear force at C right, shear force at C right, it will be nothing but when the unit load is in C in the left hand side and right hand side if you calculate. So it will be nothing but L minus Z by L. That's why the shear force at C left, that is minus Z by L. So we have drawn the straight line. So at A shear force is 0. So here it is minus Z by L. Immediate right it will be L minus Z by L, and at B it is 0. So you can draw the points. You can connect the points, and this is your final influence line diagram for shear force at C. The similar way, if you find out the moment, at C, the moment at C will be Z into, your reaction is nothing but L minus Z by L into Z. Okay, so Z into L minus Z by L. So your moment at B is Z into L minus Z by L. So here the moment is 0, here the moment is 0. So you can connect those, and this is nothing but your ILD for bending moment at C. I hope you understood how to construct the ILD for shear force and ILD for bending moment. So we'll see one or two examples so that you can clearly understand how to construct the shear force in the actual beam conditions. So here is the example. So let's say this beam is A and B, whose distance is the span length is 10 feet. Okay. So how to write the equation for this? Let's say the unit load is at distance x from A, and let's say we are considering here, we'll calculate moment at B is equal to 0. So if we calculate moment at B is equal to summation of moment at B is equal to 0, and here we have considered anti-clockwise positive. So it is up to you what you are considering. If you are considering clockwise positive, then you consider overall problem clockwise positive. If you are considering anti-clockwise positive, you consider the overall problem that is anti-clockwise is positive. Okay, so for the calculation purposes. So here we have considered, let's say, anti-clockwise is positive. So write the equation for this. The equation will be the moment at B. How to calculate the moment at B? So reaction at A, that is reaction at A which is upward into perpendicular distance. So it will be clockwise. So you have considered anti-clockwise positive. So clockwise means negative. So you have written negative. So minus AY into 10. Minus AY into 10. The distance is 10 feet. Then plus 1 into your unit load. 1 into what is the distance here? The distance is 10 minus x. Total length is 10. Your unit load is situated at x distance from left hand. So this distance is unit load to right support is 10 minus x. So unit load 1 into 10 minus x is equal to 0. And this is positive because it is anti-clockwise. So now what will be reaction at A? So AY is, we have calculated 1 minus x by 10. If you solve this, 1 minus x by 10. So now, in the similar way, we will see this condition. So another case. So from this equation directly we can draw this table. We can directly draw this table. So if x is equal to 0, now tell me what is the value of AY. If x is equal to 0, AY is 1. If x is equal to 2.5, if x is equal to 2.5, this case, if x is equal to 2.5 feet, so what will be the equation? Summation of moment at B is equal to 0, same equation. So minus AY into 10 plus 1 into 10 minus x, that is 10 minus 0.25, so 7.5 is equal to 0. So AY is equal to 0.75. Same way, we have calculated if x is equal to 5, it will be 0.5. If x is equal to 7.5, put that value in the equation here, you will get 0.25, and x is equal to 10, it will be 0. So you connect all the dots, whatever points we have identified depending upon the x values, and if you connect, it will be the influence line diagram. Okay, so this straight line equation is AY is equal to 1 minus 1 by 10 x. I hope you understood how to construct the influence line diagram per reaction. Next, we'll see how to construct the influence line for vertical reaction at B. Vertical reaction at B. Let us consider this particular example. There is a beam. So this is end A and B. So A, B, B is there. The distance between A and B is 5 meters, and here also 5 meters. So if point load is or unit load is a distance x from left support. Okay. So how to draw the influence line diagram? So draw this diagram and let us calculate the summation of moment at A is equal to 0. Write down the equations. So what will be the equations? By, we are calculating summation of moment at A is equal to 0. So by into perpendicular distance 5 meters. So by into perpendicular distance minus 1 into x. 1 into x. So minus 1 into perpendicular distance is x is equal to 0. So what is the value of by? By you got x by 5. So by is x by 5. Now I will draw the table at different x values. What will be the value of by? If x is equal to 0, Dy is 0. If x is equal to 2.5, so put the value of x is equal to 2.5 here, so 0.5. If x is equal to 5, x is equal to 5 means point load is at on the point B. So if x is equal to 5, what will be the reaction at B? So here at x value put 5, so 5 by 5 that is 1. If x value is 7.5, so we got it 1.5. If x value is 10, so it will be 10 by 5 that is 2. So now at x is equal to 0, 0 x is equal to 2.5, it is 0.5, it is 1, 1.5, 2. Like this, if you connect the points or dots, we can draw the influence line diagram for dy. And the equation is here 1 by 5 into x. Right? We'll move to another example how to construct the influence line for shear force at C. So this particular case we'll see. Here is the beam is given A and B. The distance between and here it is C, A, C, B. Let's say this is D. So all are 4 meter distance, A to C, C to B, and B to D. Right? So write down the equations now. So what will be the equation? Reaction at A. What will be reaction at A? RA and RB. So reaction at A. Let us just take the moment at A is equal to 0. So RB into perpendicular distance, that is RB into 8. RB into 8. Let's say the point load is at distance x from point A. So RB into 8 minus point load is, that is your unit load, 1 into x. RB into 8 minus 1 into x is equal to 0. So what will be RB? RB is equal to x by 8. Right? So what will be RA? RA will be 1 minus x by 8. So RA will be 1 minus x by 8. RB will be x by 8. Okay. So now we are calculating shear force at A. Shear force at A. So this condition you look into. So we have calculated now reaction at A. Reaction at A is 1 minus x by 8 or 1 by 8 into x. So here shear force and bending moment will be developed. Now what is this particular condition? This particular condition is when x is in between 0 to 4 meter. When your unit load is moving in between A to C, that is 0 to 4 meter. So what will be the shear force? Shear force at C. What is the shear force at C? If you calculate in this particular case, shear force at C, shear force at C will be your, how many forces are there in left hand side you see? What is shear force? The algebraic sum of all the forces we are calculating either left or right of the section. So we are calculating at C. So let us calculate from left of the section. So how many forces are there? One is reaction at A, another is our unit load. So now calculate. So upward direction will consider positive, downward direction will consider negative. So if you consider that, so what will be shear force at C? Shear force at C will be RA minus 1. That will be the shear force. So RA is nothing but 1 minus x by 8 minus 1. So 1 will be cancels out. It will be minus x by 8. So the shear force at C is equal to minus 1 by 8x. When the unit load is moving it between 0 to 4. Okay. So now we'll see when the unit load is moving in between 4 to 12. 4 to 12 means from here to here. When the unit load is moving from C to D, let's say. Okay. So what will be shear force? Same condition you look into. This is the second condition. Now your unit load is not in between A to C. Okay. So unit load is not in between A to C. It is somewhere in between C to D, right? So what will be the equation now? Shear force. So shear force at C will be how many? Same way you calculate from the left hand side. So what is the force here? 1 minus x by 8, right? That is shear force. So here shear force is 1 minus 1 by 8x. Okay. Now we have got two equations. Okay. So we'll put it here. What is the value of x? Let's say the value of x is equal to 0. That means your unit load is on point A. The shear force at C is, put it here, the x value is 0, so it is 0. If the x value is 4, okay, if the x value is 4, what is the value here? In this equation you put, it will be minus 1 by 8 into 4, so minus 0.5. If you put the same equation, x value is 4, so what will be the value of shear force at C? 1 minus 4 by 8, that is 0.5. So 1 minus 0.5 is 0.5. So two values you are getting, C left and C right. So this is 0.5. So when you put the value of x is equal to 8 in this equation, 8 means now your x is 4 to 12. So in this equation you'll put. So 1 minus 8 by 8, so it is 0. When x is equal to 12, that means when the point load is at D, put the value of x is equal to 12 here, we'll get minus 0.5. So now we'll plot the influence line diagram. So here it is 0, here it is minus 0.5, the C right it is 0.5, and when it is x is equal to 8, the value is 0. When x is equal to 12, the value is minus 0.5. So we'll connect the points, connect the points, connect the points, and we'll get the influence line diagram for shear force at C. I hope you understood how to calculate the shear force at C, and by taking the point, the position of the unit load, we can record the responses. What is happening at the shear force at C, on the shear force at C. Okay. Next, we'll see one example, that is how to construct the influence line for the moment at C, the bending moment at C. The same example we'll take. Same example we'll take. So here it is point A, here it is point C, here it is point B, and here it is D, and 4-meter distance, all 4-meter distance from A to C, C to B, and B to D. Okay, so now we'll write the equation for bending moment. So what is the reaction we have calculated in the previous example? Reaction at A is equal to 1 minus x by 8, and here the reaction we have calculated x by 8. So what is the moment at C if the point load is here somewhere in between, and x distance from left end unit load? So what will be the bending moment at C? Bending moment will be, so Ra into the perpendicular distance. So that is Ra into perpendicular distance, that is 1 minus x by 8 into perpendicular distance is 4, minus 1 into what is the distance? This distance, 1 into perpendicular distance is 4 minus x. Yes or no? Is equal to 0. So this is your moment. This is your moment at C, right? So if you simplify this, so 4 minus 4 by 8, 4 by 8 nothing but 1 by 2. Okay, into x minus 4 minus plus x is equal to 0. So in that case, 4 will be cancels out. So x by 2 minus x by 2 plus x, right? So this is the moment. not 0, will not put it 0. So my x minus x by 2 is nothing but x by 2. So moment at C is x by 2 when, what is the condition? When the unit load is moving in between 0 to 4. When the unit load is moving in between 4 to 12, if you calculate the moment at C, so this case you see, so in this case, the moment will be this reaction at A into perpendicular distance, that is 1 minus 1 by 8x into 1 minus 1 by or x by 8 into 4. So it is 4 minus x by 2. 4 minus x by 2. So moment at C when x is moving in between C to D, right? So now we'll construct the table with respect to x and MC, moment at C. If x is equal to 0, put the value here. What will be the moment at C? X is equal to 0. Moment at C will be 0. If x is equal to 4, that means the unit load is on the point C. Unit load is on the point C. So x is equal to 4. That means put the value here 4. So 4 by 2 is 2. Okay. So when x is equal to 8, x is equal to 8 means your unit load is in between 4 to 12. So here in this equation we'll put the value x is equal to 8. So 8 by 2 4, 4 minus 4 it is 0, and x is equal to 12. X is equal to 12 means 12 by 2, that is 6. So minus 4 minus 6 is minus 2. So now we'll connect the values. X is equal to 0, so this value is 0. X is equal to 4, the bending moment is 2. X is equal to 8, the bending moment is 0. And x is equal to 12, the bending moment is minus 2. So if you connect the points, we'll get the influence line diagram for bending moment at C. Right? I hope you understood how to calculate the influence line diagram, how to construct the influence line diagram depending upon the position of unit load, which is very important. It's a basic things because it will require in the calculation of different reactions, ILD constructions of reactions, ILD constructions for bending moments, ILD constructions for shear forces. Okay, and when the complicated loading conditions will come, let's say your series of load will come or UDL will come. So at that time we have to calculate actually in very quick. We have to calculate. So this is the detailed steps, detailed procedure how to construct the influence line diagram if there is a point load is moving from one end to another end of the beam, right? So if you have any doubt, you can ask. Otherwise, so here is the summary. You can go through the summary. What is the importance of influence line diagram? Okay, and how to calculate or how to construct the ILD, which we have already discussed. So next class we will see how to construct the ILD if there is a simply supported beam and it is